Hello, I'm Lorenzo Sabattini from the University of Modena Reggio Emilia, Italy. In this paper we propose a method for the teleoperation of a multi-robot system in which we consider a master device directly connected to one of the robots at the slave side. So the force feedback provided to the human operator is given by a combination of the coupling forces among the robots and the contact forces with the environment. So we want to propose a method for reducing the disturbing effect of the coupling among the robots and providing then a force feedback that is only given by the average interaction forces with the environment. So one solution could be to uniformly scaling down the couplings among the robots. In this way we would obtain the desired force, but we would have the disadvantage of making the system unnecessarily loose, thus decreasing the performance of the system. Our idea is to scale the forces only locally, so reducing the perturbation with respect to the nominal behavior. So the coupling that we are considering is the following, in which we have the position of the mass that is used to control the velocity of the slave. So the force feedback that is provided to the operator is given by the inertia, damping, and the coupling forces among the robots and the external forces that represent the contact with the environment. We propose to introduce scaling factors to adjust this force feedback. In the paper we prove how to do that in a passivity preserving manner using Porte-Hamiltonian formulation and the concept of energy tanks. So the desired force feedback is that of a floating mass subject to a certain damping coefficient plus the estimated average contact forces of all the robots. So we propose to implement a constraint optimization problem for the selection of the tuning gains in which the constraints are imposed to satisfy passivity preservation. In order to validate the proposed strategy, we implemented some teleoperation experiments, first in virtual reality environment. In these experiments, we compared three situations, one where we have high coupling gains among the robots, then low coupling gains, and variable gains computed according to the strategy proposed in this paper. Here we see that with high coupling gains, the system is difficult to be teleoperated since it becomes very slow due to the high forces. Now we see that if we use low coupling gains, we have a high dispersion of the robots, which makes the teleoperation difficult in a cluttered environment. So the proposed variable gain strategy represents a nice trade-off between these two extreme conditions. We also implemented some experiments on real robots using a group of EPAC robots where we obtain similar performance. Thank you very much for your attention. See you at the post.